Hi everybody, I hope this video finds you well. Today we're going to be working through section 2.5 from your textbook, which discusses the solving technique known as Gaussian elimination. Now, we're going to do section 2.5 in two videos, and the way we're going to sort of separate this is that in this first video here, we're going to talk about the sort of computational side of Gaussian elimination. In other words, we're going to run through a couple examples of using matrices, augmented matrices, and row echelon form to actually solve systems of linear equations. Then, in the next video, about section 2.5, we'll go through the sort of theoretical considerations about the solution sets and how concepts like the rank of a matrix actually help us understand the type of solution set we're going to get for a system of linear equations. So we're going to be doing sort of two pieces for section 2.5. This video will be on the computational side of things, and the next video will be on the more theoretical side of things. So let's talk about this technique called Gaussian elimination. Gaussian elimination is basically a way of using what we discussed in the previous videos about taking systems and rewriting them as augmented matrices, and also about how to reduce a matrix into row echelon form. So, the main idea for solving a system of linear equations using Gaussian elimination is, well, you first start with a system of linear equations. Then you take that system of linear equations and you rewrite it into an augmented matrix form. Remember, an augmented matrix form is going to be the matrix of all the coefficients, then that little vertical line that sort of separates it visually, and then a column for all the sort of constants that are what the system is equal to. So we'll rewrite it into augmented matrix form. Then we're going to use elementary row operations. Remember, we have three elementary row operations. You can interchange or permute two rows. You can multiply any one row by a non-zero scalar. And you can add a non-zero multiple of one row to another row. Those are your three elementary row operations. So you'll use those elementary row operations to put the augmented matrix into row echelon form. If you put it into row echelon form, you're technically doing what's called Gaussian elimination. If you go all the way to reduced row echelon form, remember reduced row echelon form requires that all elements above a leading one are also zero, then you're actually running what's called Gauss-Jordan elimination. For this class, it won't matter which technique you use. Your textbook sometimes asks you to do one or the other, but for our class, we'll just sort of do whichever one is convenient for us, most of the time just doing Gaussian elimination. Then the idea is that once you are in that row echelon form or that reduced row echelon form, you should be able to use back substitution to solve the resulting system. And all we mean by back substitution is to take the sort of last leading one row and use that to solve for one of the variables. Then, since we have one of the variables, we can put that back into the next equation and solve for the next one, so on and so forth. And we'll see some examples of that. So we're going to see how to implement this little algorithm here. You should keep in mind that this really is an algorithm, especially since putting something into row echelon form, in the last video, we developed an algorithm to do that. So you can imagine that Gaussian elimination is a very easy thing to sort of program a computer to do. So massive systems of linear equations can be handled very easily through computers since we have a direct algorithm to handle them. But we're just going to do a couple examples by hand to sort of see how this works. All right, let's go ahead and take a look at our first one of these examples. So we're going to try to solve this system. So we've got a system that has three variables and four equations, right? So the first equation says that 2x1 minus x2 plus x3 must be 7. Second equation, x1 plus 6x3 needs to be 3. 3x1 plus 2x2 minus 2x3 has to be 7, and then 6x1 plus x2 plus 5x3 equals 17. So let's go ahead and first just translate this into that sort of augmented matrix form. So what is this guy going to look like? Well, that first row is going to be 2 minus 1, 1 for the coefficients thing. Then 1, 0, 6. Then 3, 2, negative 2. And then 6, 1, 5. Then we'll put our little vertical line there and put our constants that are equal to 7, 3, 7, 17. So that is the augmented form of this, right? Now it's just a little bit of sort of notation since it's our first one. This guy here, this matrix would be considered what sort of is A, and then this entire thing is A augmented, which we often write with a little like hashtag symbol. So A with that little hashtag symbol indicates the augmented matrix, whereas A represents just the sort of matrix of the original coefficients here without these pieces. Okay, so now our goal is to take this thing and try to put it into row echelon form. Now again, you can do this in a lot of different ways. So I'm just going to follow one approach that sort of pops out to me, and then if you see a different way and you get to the same answer, obviously that's totally fine. What I'm going to do though is I want a sort of leading one. I mean, we can sort of see that this is our first non-zero column, so we're going to need to use that. Now, of course, I could just divide everything in that first row by 2, but notice that that's going to introduce a lot of fractions, which are fine if you're comfortable with them, but you might as well sort of spare yourself that by just shifting this second row up to the first row. So let's go ahead and do that. What I will do is I will interchange row 1 and row 2. And again, I would really like, when you guys do this, to keep track of your operations like this with some notation. All right, so let's go ahead and see what we get there. We get 106, 2, and might as well just bring that along, 1063, 2, negative 117, and then everything else stayed the same. 61517. All right. Now, what we're going to do is that since we've got our leading one there, we need to clear out everything below it. Now, what I would recommend here is that as you guys get more comfortable with this, you can do several operations at once. So what we're going to do on the next one is we're going to take row 2 and we're going to replace it with row 2 minus 2 row 1. That will help us remove this guy right there. But we can also take row 3 and replace it with row 3 minus 3 row 1. And we'll take row 4 and replace it with row 4 minus 6 row 1. Now, this is technically 3 different elementary row operations, so technically we should do this guy, write out the matrix, then do this guy, write out the next matrix, and this guy. But again, for our sake, since we can handle multiple operations at once, unlike maybe a computer, we can go ahead and do this all in one piece. Again, this is why it's so important that you show this so that somebody can follow along what operations you're doing. So let's go ahead and do that. None of these operations affect that first row, so we can just keep that the same, 1063. All right, now we're going to take row 2 minus 2 row 1. So that's going to zero out that first component. Then it's going to be minus 1, and then 1 minus 12, so it should be negative 11 there. And then 7 minus 6, so we'll get 1 there. Okay. Next one, we're going to take row 3 and replace it with row 3 minus 3 row 1. Of course, that's going to zero out the first component. That's why we chose to do it. Then we've got a 2 there, and then negative 2 minus 3 times 6. So negative 2, and what is that? Negative 18. So that sounds like negative 20 there. Yep, that sounds good. And then 7, 7 minus 9. Yep, negative 2. All right. Going along pretty good so far. And then the last one, we get that 0 there, then 1, and then 5 minus, sounds like 36, so negative 31, and then 17 minus 18, so negative 1 there. Okay, so there we go. There's our new matrix, and we did at least get the start of what we want for row echelon form. We've got that leading one, and we've got all zeros below it. Now, our next non-zero column would be this guy here. This is that sort of pivot position. He's in good shape, except that he's a negative 1, so we can fix that real quick by taking negative 1 times row 2. So let's see what that'll look like. That means we'll now have our matrix 1, 0, 6, and 3. So we're not touching that guy at all there. Then 0, 1, 11, and negative 1, and then nothing else is being impacted. Okay. All right, looking pretty good. Now, this is good. This is a leading one. We just got to zero out the things below it. So let's do those operations. We'll take row 3 and replace it with row 3 minus 2 row 2. And we'll take row 4 and replace it with row 4 minus row 2. And let's go ahead and see what that's going to look like. All right, so first row not going to change at all. Second row also not going to change. And our third one is being replaced with R3 minus 2R2. So it looks like we should get 0, 0, and then negative 20 minus, 22? So I guess that's negative 42 there. And then negative 2 plus 2, so that sounds like 0. And then we get R4 minus R2, so that'll give us 0, 0, negative 31 minus 11. So that's also negative 42. And then negative 1 plus 1, that's going to be 0 there. All right. Things are looking pretty good there, right? We've got a couple leading ones. We've got zeros under everything there. All right. Now, our next non-zero column is here. This is our sort of pivot position. Obviously, that negative 42 is going to have to go. So we're going to do sort of, I guess, a weird-looking operation. Negative 1 over 42 times R3, but it won't be particularly hard to do that. 1, 0, 6, and 3, 0, 1, 11, and negative 1, 0, 0, and 1. And of course, when we do that negative 1 over 42 on the 0, well, that's going to be 0 as well. And then we get 0, 0, negative 42, 0. All right. Finally, we need to zero out anything below this guy here. So I guess we can do the sort of weird thing of taking R4 and replacing with R4 plus 42R3. And that will give us this matrix, 1, 0, 6, 3, 0, 1, 11, negative 1, 0, 0, 1, 0. And of course, this will be 0, 0, 0, 0. All right. So this now is in row echelon form. So this is not, of course, the solution, but this gives us a very easy system to sort of back solve. So to back solve, we'll start with the sort of first non-zero equation here. So we've got this guy right here, and that will break down into telling us that x3, well, let's maybe write it out so you guys can see how we're getting at. If we sort of reverse this, right, this equation here, that guy there should be 0x1 plus 0x2 plus x3 is equal to 0, which of course tells us then that x3 is equal to 0. So that's one of our variables there. Now we can go grab the next equation, sort of backwards here, and that tells us that 0x1 plus x2 plus 11x3 is negative 1. But we know that x3 is 0, so we can pop that in. This tells us that we get x2 plus 0 is negative 1. And this tells us that x2 is negative 1. So now we have x2 and we have x3, and we can use this sort of last equation up there and say that x1 plus 0x2 plus 6x3 is supposed to be 3. But we know x2 and x3, so this becomes x1 plus 0 is 3, which tells us that x1 is equal to 3. So our solution here is we've got one unique solution, x1 equals 3, x2 equals negative 1, x3 equals 0. So we have one unique solution. Okay, there we go. All right, so were there ways that we could have sped this up? Yeah, probably, right? Right here when we did this operation, right, we might as well have also done it on this guy so that we didn't have to have this awkward negative 42 there. It ultimately didn't matter much. We could have also just sort of right here said, why don't we just take this row 4 and subtract row 3 to immediately just zero that out. We could have done that as well, right? So again, I did this example very sort of algorithmically. But you guys, of course, when you're solving these, if you see sort of faster steps, as long as you're following those elementary row operations, you should be all good there. So feel free to solve these as you want. We don't have to solve them according to the strict algorithm. Now, I do want to make one comment about the fact that this came out with one unique solution. And I want to tie that in a little bit to sort of some of the comments that we made about rank. So I want to make a note here, just down here, note. If we look at this, when we went through and we took this matrix A and A augmented, and we went all the way down to the sort of row echelon form, remember row echelon form allows us to talk about rank. So if we look at this section right here, you'll notice that that tells us that the rank of A was 3. Because when we actually took just this part over here and we looked at the number of non-zero rows, there would be 1, 2, 3 non-zero rows. What can we say about the rank of A augmented? Well, the rank of A augmented, if we include this portion here as well, then there would be non-zero rows, 1, 2, and 3. So the rank of A augmented was 3. And what I want to notice as one sort of last component is that the number of variables, right, if we go back to the original equation, was 1, 2, and 3. And so if you think about calling that like m by n, that would mean that n was 3 here. Now, it doesn't necessarily seem like a coincidence that we got this one unique solution when this very sort of unique thing happened, when the rank was the same as the augmented rank was the same as the number of variables. In our next video, we will actually show that if this is the case, then we are guaranteed to have one unique solution. All right, we've got a couple more examples to try. We're going to run through those other examples a little bit more quickly than we did on this one. But at the end of the other examples, we will do this same consideration about this idea of the rank of the augmented matrix, and the number of variables. All right, let's take a look at solving this guy. So we've got a new system to solve. First step that we're going to do is immediately just put it into that augmented matrix form. So as an augmented matrix, this would be 3, 2, negative 1, 1. And then that vertical line and 2, then negative 1, 4, 2, negative 3, and 5, 4, negative 2, negative 3, 4, and 3. Okay, so we've got some things to definitely do here. I like this guy right here as coming up, so I'm going to begin by interchanging row 1 and row 2. So that'll give us a new augmented matrix, negative 1, 4, 2, negative 3, and 5, and then 3, 2, negative 1, 1, 2, and then 4, negative 2, negative 3, 4, 3. Okay, we should fix that first row, so we'll do negative row 1, and looks like we should get 1, negative 4, negative 2, 3, negative 5, 3, 2, negative 1, 1, 2, 4, negative 2, negative 3, 4, 3. Okay, so we're all good there. Now we can start using this pivot position here to clear out the things below. So let's go ahead and do that. We're going to do row 2 minus 3 row. Oh, that's not quite the notation we've been using. So let's replace R2 with R2 minus 3R1, and we'll replace R3 with R3 minus 4 row 1. Now, do keep in mind, one thing that does happen sometimes as a mistake if you're working through this is to like replace row 2 with some combination of R3 and R1. That is not an appropriate row operation, right? If you're going to replace row 2, it has to be with row 2. So you're always noticing that I'm always doing R2 being replaced by R2 and some combination of another row, or R3 with R3 and some other row. So whatever you're going to replace a row with has to include that original row if you're going to be using that third elementary row operation. All right, there we go. Let's go ahead and continue on there. All right, so now that we did that, what is our augmented matrix going to look like? Well, 1, negative 4, negative 2, 3, and negative 5, because row 1's not changing. Row 2 minus 3, row 1. It's going to give us a 0 there. And then 2 and looks like 12, so 14. And then negative 1 and 6, so it sounds like 5. And then 1 and looks like negative 9, so negative 8. And then 2 and 15, so 17 there. All right, and then in the other one, we'll get 0, and then negative 2, and what is that, 16? So that's a 14. -3 and 8, so that's going to be 5. And then 4 and -12, so that's going to be -8. And then 3 and, what is that, 20? So 23. Okay. Sorry about that. There we go. All right. Now, at this point, right, this is a good moment to sort of recognize that we probably want to go ahead and use like a non-algorithmic moment here. We are sort of aware enough as humans to see that these two sort of match, and we should probably use that to our advantage right away. So before we would normally go ahead and like divide by 14 or something, but let's go ahead and just first use that sort of recognition there. So let's go ahead and take row 3 and replace it with row 3 minus row 2. So if we do that, we would get 1, -4, -2, 3, and -5, 0, 14, 5, -8, and 17. And then we would get 0, 0, 0, 0, and then 23 minus that 17, which sounds like 6. All right, so this is sort of unique. We get something that looks like that. Now, if you think about actually taking that equation and sort of pulling it out, that tells us that 0x1 plus 0x2 plus 0x3 plus 0x4 is supposed to be 6, which of course is impossible. So what that tells us is that there are no solutions here. So if you ever get something like this, where you have a 0 row and then a non-zero value there, that means there's going to be no solutions. And remember, the sort of fancy name we gave for that was that this can be called inconsistent. So let's see what happened in terms of rank that might explain this inconsistency. So if we look back and we look at sort of the matrix A, this guy here, well, we followed this down to here, right? He's not quite in row echelon form here, but of course dividing by that 14 would show us that there's going to be those 2 rows there. So if we make a sort of note here, the rank of our actual matrix was 2. What about the rank of the augmented matrix? So if we use the whole thing, well, the whole thing would be here, and you can see that the rank of that is going to be 1, 2, and 3. It has a different rank because this would be a non-zero row for the augmented matrix. So the rank of the augmented matrix was 3. So what you guys want to sort of see here is that the rank and the rank of the augmented matrix were different. And that turns out to be exactly the condition that tells us when we're going to have an inconsistent system. And that should make sense, even just in this one example. How is the augmented matrix going to have a different rank? Well, it's going to have a different rank if there's sort of a 0 row here, which doesn't contribute to the rank here, but a non-zero value here that does contribute to the rank of the augmented matrix. But if you have all zeros here and a non-zero value there, that's always going to give you an impossible system, which means it's always going to be inconsistent. And we'll prove that in our next video. All right, we've got one more example to sort of try here. And again, we'll make some comments about the rank at the end. All right, we're going to solve this system here. And we'll start by just putting it directly into the augmented matrix form. So that would be 4, -2, 8, and 0. Then 3, 1, 1, and 0. And then 10, 0, 10, 0. Now, if you remember, right, this is what we called a homogeneous. That looks terrible. You won't be able to read that at all. Let's try that again. This is what we called a homogeneous or homogeneous system because it is equal to all zeros over there. Now, before we even start this, without even solving it, I know that there's a solution here. And it's not just because I wrote the actual problem. I know that there's a solution here because it's homogeneous. How do I know that? Well, since everything's equal to 0, just imagine letting every variable be 0. If every variable is 0, this will be 0, 0, and 0, which will be 0. This will be 0, 0, and 0, and this will be 0. And this will be 0, obviously 0, 0, and that'll be 0. So whenever you have a homogeneous system like that, there's always going to be a solution. There's always going to be 0, 0, 0 as a solution. The question is, are there any other solutions? But keep in mind, this guy's got to be homogeneous this time. Or this guy's got to have a solution because he's homogeneous. All right, let's see if there's any other ones by actually going through our system here. Now, it might not necessarily look it, but I actually like this row because I can change those into ones and won't introduce any fractions. So I'm going to go ahead and start by interchanging row 1 and row 3. So that gives me 10, 0, 10, and 0. Then 3, 1, 1, and 0. And then 4, negative 2, 8, and 0. All right, then we go ahead and we take 1/10 of row 1. So we can get that to be 1, 0, 1, 0, 3, 1, 1, 0, and 4, negative 2, 8, 0. Okay, now we've got that sort of pivot position 1, so we'll use that to clear out stuff below. We're going to take row 2 and replace it with 3. Let's go ahead and erase that, not 3 yet. We're going to take R2 and replace it with R2 minus 3R1. And we'll take R3 and replace it with R3 minus 4 row 1. So doing that, we should get, sorry about that, don't need another squiggly line. I already got my squiggly line. Can't have too many squiggly lines. Well, maybe you can, who knows, right? That's just idle talk as we fill this stuff in. Okay, there we go. 1, 0, 1, 0, and then we're subtracting R2 minus 3, R1. So that's going to be 0, 1, and then 1 minus 3 there, so negative 2. And of course, it's going to remain 0. And then here, we're going to get 0. Negative 2 is going to remain as negative 2. And then 8 minus 4 is going to be 4 there, and 0. All right. Well, this guy nicely is already got a leading 1, so we'll just use him real quick to zero out that. So we'll take R3 and replace him with R3 plus 2R2. And we'll get 1, 0, 1 with a 0. Then we'll get 0, 1, negative 2 with that 0. And then we'll get 0, 0. 4 and negative 4 is going to be 0 and 0. All right, now this is in that row echelon form, so we'll go ahead and back solve, right? Notice that we're not going to be able to look at this guy, but we're going to have to actually look at this guy. So if we do that, that would give us x2 minus 2x3 is supposed to be 0. Now, normally when we start off back solving, we immediately get one where we can solve x2 equals something, or x3 equals 5 or something. But this time, right, we're getting a relation between these two variables. So what we're going to have to do is we're going to have to introduce a sort of free variable or a free parameter. And the way that we sort of always do this is we avoid introducing that free parameter for things that actually have those leading 1s. So you can see these leading 1s are on x1 and x2. So what we're going to do is we're going to let x3 be some free parameter t. So if we do that, then this becomes x2 minus 2t is 0. And then that implies that x2 is going to be 2t. So if we can choose anything for x3, but whatever we choose for x3, x2 has to be twice that. Now let's go to our other equation, right? We got to still find out something about x1. So in that guy, x1 plus 0x2 plus x3 is 0. We still have this let x3 be t, so we get x1 plus t is 0. And that tells us that x1 is negative t. So what we have here is we have our solution set is infinite solutions of the form the form of these solutions is that x1 has to be negative t, x2 has to be 2t, and x3 can be any value t. Now, just to help you guys sort of understand what that sort of means is examples of those solution sets would be something like, okay, let's say t is 5. So it would be x1 is negative 5, x2 would be 10, and x3 would be 5. Or you could have something like, let's say t is negative 3. So then x1 would be 3, x2 would be negative 6, x3 would be negative 3. So there are infinite solutions, but there's still a restriction, right? You can choose anything you like for x3, but then x1 and x2 are determined by that choice. All right, so this guy had an infinite solution set. Let's see what we can say about the rank. So let's look back at our matrix A here, ignoring sort of the augmented part. This guy eventually turned into this, and you will see that he had a rank of 2. So let's make our little note here. Note, rank of A was equal to 2. What about when we actually had the augmented matrix? Well, that became this. There was this row down here, but it was a 0 row for A, and it was a 0 row for the augmented matrix. So the rank of A augmented was also 2. So notice that the rank of A and the rank of A augmented are the same. We saw that that wasn't the case here, and it was inconsistent. And we saw that that was the case here, and there was a solution. So that sort of hints at that what the rank and the rank of the augmented matrix are the same, you have a solution. The difference, though, in our example, is that the rank here is 2, the rank here is 2, but the number of variables, n, was 3. So these two, while they were equivalent, did not match the number of variables. But how off were they? Well, these were 2, and this was 3. So that difference is off by 1. And how many free parameters did we need? Well, we only needed 1 free parameter to explain the solution set. So that tells you guys that one of the theorems we're going to be proving in our next video is that the number of free parameters necessary is the difference between the number of variables and the rank of this matrix or the augmented matrix. So the main takeaway from this video is to make sure that you're comfortable using Gaussian elimination and back substitution to solve systems. In the next video, we'll formalize these comments about the rank into a couple major theorems about the solution sets of systems of linear equations.